Good afternoon. This is Derek Pizarro, Senior Product Manager with AST Environmental. We have a lot of people signed up for today, so we're just going to give them a few more minutes to log in here, and then we'll get started. Thank you. Good afternoon. This is Derek Pizarro with AST Environmental. Thank you for joining us today. My co-presenter for the presentation today is Bill Brad. He's one of our senior remediation geologists. Bill is based in Kentucky, and I'm based in Pennsylvania. Today's presentation is going to be on fractured bedrock slurry injection, best practices and applications, and what is a triplex. That's something we'll explain in subsequent slides. It's kind of our hook for today, but it's something unique, and it's advantageous to bedrock slurry injection. So I just want to say thank you, everyone, for joining us. I know these are strange and busy times, but I appreciate you carving out about 40 minutes or so for us to present to you today. So thank you very much. This RPI Group webinar series, this is the 7th installment of 8. And I definitely want to say thank you to RPI for putting these together and hosting these. Both AST, RPI, and Microbac have given a number of presentations this spring, kind of as a soup to nuts, tip to tail, a holistic approach to your site from start to finish. So if you missed any of these, all these that we have listed here are up on the website. Today's will be uploaded as well. So if you missed these, if you want to go back and look at a specific topic that we don't dive into too deeply today, that's available to you on RPI's website, trapandtreat.com, or you can reach out to Bill or myself to expound upon things that we will cover today. If you have any questions, there's a question box. Probably many of you are familiar with GoToMeeting, Zoom, Hangouts by this point. But if you're not, there's a question box there. Please enter any questions as you go throughout the presentation. And there's also a chat feature as well. I have my other colleague, Mike Mazzarese, who's one of our senior engineers based in Colorado. He'll be monitoring those and also running the Q&A session for us as moderator. So just a quick brief overview of RPI Group. RPI is based in Golden, Colorado. They formed this group in 2011 basically to come up with best practices for the installation of their products. These are true slurries, so we had to adapt a lot of the concepts that most of us commonly use as practitioners day in and day out to adapt those products to use in bedrock and overburden transition zone settings, even in some cases possibly yellow iron settings. So we work collaboratively as a group. At AST, we are in charge of project assessment and design. We also do QA and QC, and we distribute the product within the authorized installer network. In terms of the network, this is a group of companies that RPI and AST have vetted. They've received specific training to the installation of these products, and that's something that we work on very carefully here to make sure that as you see this, the approach we're showing you here today and in other webinars, that you see a complete quality high performance installation, whether it is bedrock or overburden or another setting. Just a quick footprint here. Obviously, we have a vast experience here in the U.S. and North America as well. But we've also been some really neat places with this technology, including parts of Scandinavia, Africa, the Caribbean, and Europe. So don't think just because you're watching this presentation today that we can't adapt this and take this to places outside of the continental U.S. So briefly here's our roadmap. I just got through an introduction. The three main segments here today are going to be the RDC for Bedrock. That's an extremely important component. We're going to spend a decent amount of time on that. And then obviously the next most important part of this is the installation. There's going to be some equipment covered in both of these that is possibly familiar to you. There's some equipment that is unique to AST and RPI Group that's not available elsewhere in the industry right now. So you'll see some stuff that's definitely new to you. And then we'll finish up with some examples and performance monitoring to describe how these work in situ once they're installed. So to get into the Bedrock RDC process, I'm going to hand this off to my colleague, Bill Brab. But if you've joined us for other presentations, this is kind of a modified approach to a traditional overburden RDC. Obviously, the tools and the access are going to be vastly different than an overburden unit with something like direct push. But we adapt this process to fit in Bedrock. And Bill, if you're on the line here, come on in and you can take over the RDC.
Yeah, thank you, Derek. Can you hear me okay? I want to thank you for the introduction. Again, same as Derek has said, I want to thank everybody for taking time out of your busy schedule to listen to what we have to say today. Also thank RPI, Microvac for their contribution to this program as well. And if you've been with us, like Derek said, with previous presentations, webinar series during this season, we're going to follow this roadmap to success on pretty much any site that you're going to be involved in with environmental remediation. And essentially it involves, we'll just go through this fairly quickly, an upfront review, looking at the existing conceptual site model and coming up with a preliminary plan based upon this information. And usually during that initial review, we identify data gaps or information that's needed to be filled in order to have a higher level of confidence and ability for success when remediating a facility. And that's when we'll propose an RDC, stands for Remedial Design Characterization. Essentially, this is a trip to the site or multiple trips to fill in those gaps with additional sampling or investigation work and characterization. We then compile all that data to come up with a more effective redesign or a new design based upon the updated, more accurate conceptual site model. Moving forward from there into field implementation and then post-performance monitoring to evaluate the effectiveness from there. Derek, next slide, please. So when we evaluate a site or have a project come across our desk and start evaluating the initial conceptual site model, in most cases, the initial review and preliminary design notes some concerns, especially when we're dealing with a bedrock scenario. And dealing with some of these concerns, one of or several of the key pieces that step out in our review of it that needs to be clarified is that a lot of the wells of the monitoring network are cased wells with constructed filter pack with very long screens, essentially spanning multiple intervals of water-bearing aquifer matrix. The groundwater itself has not been really effectively characterized, looking at additional chemistry or preferential flow path or zones of high or low concentration, and then looking at the aquifer matrix itself. The lithology is typically logged from chips during air rotary. You need rock cores to get a more accurate characterization of that specific geology. It'd be like trying to log a soil from cuttings coming off of a hollow stem auger. And so the preliminary designs in response to that are typically biased high in some way because there's no differentiation of the high or low concentration intervals yielding what you're seeing in that well. We're estimating the porosities and the hydraulic gradients based upon published data or generalized data based on, again, this kind of gross evaluation of what we see coming out of the hole, assuming a homogeneous stratigraphy, which, as we all know, is not super common in the environment, but it does occur. But in most cases, it's not present. And then looking specifically at groundwater mass only. So looking strictly only at the dilute side of the plume or the contaminant present within the subsurface. Next slide, please. So moving into the first step of the RDC, one of the things that we want to evaluate, and this is a scalability situation here. So if we've got a fairly large site where we have to be strategic about borehole placement, either vertically or horizontally, one of the tools that we may want to use is a surface geophysical method or a series of methods to try and help identify zones of interest vertically, but also horizontally across the site. And several of the methods that we like to utilize for our purposes would be two-dimensional electrical resistivity combined with induced potential. And the plots on the right-hand side of your screen that you see here, the ER is on the top of the screen, the induced potential is on the bottom. The other method to assist with evaluating geologic contacts where we may have noise or interference from superficial features would be using a multi-channel assessment of surface waves, or MASW. This is essentially using a seismic method to look at the difference in the geologic materials. And so that image on the bottom part of the screen, there's a little bit of a legend key that identifies the different values for the respective zones, but that image is overlaid onto the IP and ER line. You can see the two vertical lines from the bottom side of the screen where that ties in. And there was some noise in this particular image from the pump island at the facility. So the MASW helped to fill in the gap of what we couldn't really see below that zone of interference. So for those that don't know, electrical resistivity is inducing current into the system and looking at the resistive properties of the material. And then the induced potential is looking at the bleed off or the response of electrical dissipating from essentially a capacitance of the formation itself. These are valuable for seeing different chemical or geologic properties, but also looking at properties of different material within that aquifer matrix. Next slide, please. So again, as I talked about, on a larger site, that geophysical methods, the surface geophysical methods would be valuable for helping to site boreholes. Smaller sites, you may not be able to utilize that because of accessibility and noise that would be counterproductive to the project. So using that data, we would select location of boreholes or move forward straight into installing boreholes based upon accessibility that we know from the limited access of the site. And during this drilling process where we site these boreholes, one of the pieces that we would like to have, as noted earlier, are rock cores. And this is similar to pulling a dual tooth sample prior to advancing hollow stem auger. We can look at the structure, texture, and variation of the lithology in log perspective, and we can preserve that and keep it available for our review at a later time when we come back to the site. We can also collect matrix samples and perform standard chemical tests on that for contaminants or forensics. And then once we move out of the rock coring phase of this drilling, we're going to set new wells for the purpose of characterization and injection later. These are surface cased wells that are socketed into rock, and then we have open borehole into the consolidated lithology below and leaving that borehole open for the purpose of additional interrogation at later times. These are multi-purpose access ports. They're not just looking at dilute chemistry across a spanned interval. We're going to be able to look at specific features within this subsurface unit. Next slide, please. So after the boreholes are installed, we talked about geophysical methods earlier on the surface, but now let's interrogate that hole from within a little bit closer. And so downhole geophysical tools are relatively inexpensive when you're looking at the standard details like caliper, natural gamma, resistivity, and conductivity. But then you can add in some additional tools that provide additional detail like optical televiewer or acoustic televiewer. And so 3-arm caliper is going to provide, detail of bore aperture and any variability in that. So if you've got washout zones or discontinuities that you encounter while moving through it, you're going to be able to see that as a graphical log showing bore aperture. And then looking at the natural gamma properties and the resistance and conductivity of the formation itself. Optical televiewer is essentially a camera that's going to look at looking for geometry of planar features within that borehole. Similarly with acoustic televiewer for the purpose of zones where you have water that's not clear. And then heat pulse flow is going to be looking at variable flow within the borehole itself. So looking for sinks and discharges within the hole and potential movement throughout the borehole where you may have water moving from one interval to the next. Next slide, please. And here we're going to look at a short video clip of another tool, the downhole camera. And this is a nice tool that allows us to look vertically down the borehole, but then turn 90 degrees and pan all the way around the borehole and look at it in real-time view. So we mentioned the rock core earlier, bringing that back out, having your geophysical logs in front of you where you can go to specific depths. You can note here, remember this 59.2 foot interval that we just saw in that specific image. But this is where we can use the camera to call out individual zones that we want to come back to later during both the characterization and the remediation phase. Next slide, please. So the final step of the RDC prior to coming back to the table and reevaluating is the actual groundwater or aquifer characterization, which involves a series of pumping tests and discrete analytical sampling of respective zones. And we can, again, take our geophysical plot. Here you're looking at caliper, identifying specific intervals that we are interested in interrogating a little more for characteristics of that specific interval. And as you can see, many fractures could be clustered in short intervals. And getting into one of the specialty tools that we like to use, conventional packer strings make it quite difficult to actually isolate clustered intervals like this, where you have multiple potential water-bearing units across a short zone within the borehole. So we're going to kind of work from right to left in this photo series. On the far right-hand side, you have a typical straddle packer assembly from an off-the-shelf, rental type scenario or purchase scenario where you have two single packers that are coupled together at the single juncture point. And as you inflate the packer, as you can see with the yellow marks on the inflation elements, as you inflate the packer in this particular instance, the interval for isolating discretely gets increasingly longer. In this case here, it ends up roughly at the 4-foot margin. Whereas we've had a custom packer constructed for our purposes that is dedicated for this purpose. And that interval, that's the left packer on the far right image, you can see that the yellow highlights on the packer elements maintain a distance of approximately 18 inches. You can see the blow up of that on the far left image, inflated versus deflated. And then the middle photo with the two packer strings. These are twin packers. The only difference between these two is one is for injection, which is the one on the left with the yellow shroud in the center of the discrete interval. The one on the right is for sampling purpose for the characterization. That specific interval, or that packer there, when the packer elements are inflated, there's a Triflex pump at the bottom for the purpose of drawing water from that discrete interval. There's also pressure transducer in the bottom of it that's looking at head changes below the lower inflated element. There's a transducer within that inflated interval that's looking at head change within the inflated interval. And then you have a transducer above for looking at head change above the uppermost inflated element. So essentially you can look at variable hydraulics within the borehole itself. And then looking at within that part of that characterization, we're also looking at transducer data from the surrounding well network to see the response from the pumping test and the work within that specific borehole on the surrounding unit or the surrounding geology from that pumping test. Next slide, please. And finally, the final key to this process is utilizing the RPI Project Support Laboratory in Golden, Colorado, which provides a no-cost analytical for all samples that are sent in. So this lab can analyze rock core samples for matrix analysis to look at actual aquifer matrix chemistry that we may need to look at. And then also all of these water samples being pulled from the discrete intervals in the surrounding monitoring network. And taking for the updated design, we now take all this information from the RDC, which includes the geophysics, the downhole camera, looking at the pumping test and transducer data to come up with, hydraulic conductivities and interconnectivity within the formation, both vertically and horizontally. And then using all that data, we're going to target specific secondary porosity features, whether that be bedding planes, fractures, joints, faults, solution channels, lithologic contacts, etc. Next slide, please. So moving into bedrock injection, I believe Derek's going to talk a little bit about these next slides. Is that correct, Derek? Do we want to move forward there?
Sure, thanks, Bill. So I really like this slide here. We use this in a number of our presentations, and it's really because there's a lot of assumptions that get made whenever you inject something in situ. The presence of preferential pathways exists in almost every single setting you're going to inject in. You don't get nice laminar flow in formations as much as we would like to think. So the smaller you can make an interval, the more you can isolate it, make it unique, characterize it, you can inject into it. And that all comes down to proper loading and design, which Bill just talked about. But I like this because it's just a reminder, we can't assume that as we move through every site, even if it's the same type of rock, if it's the same type of weathered rock, overburden, the same things that apply on one interval may not apply on the other. So again, going back to the RDC component here, it's very important to have a good idea of what's going on in the subsurface. Borehole geophysics are invaluable. I'm going to talk here for a second about our custom Triplex pump. And the reason for that is this is something that's so special and unique to what we're trying to accomplish in this presentation and when we go out on site for our clients. This is custom built. This is a Triplex pump. It's a 3-piston pump, which gives it its name. This is typically used in either unconventional gas, hydrofracking, or other industrial applications. It's a real big sucker. You can see it there on the right in that blue pump in the picture there in the cutout. This unit's mounted to our Kenworth T800 truck. This Triplex is 165 horsepower, and we run that off the truck's transmission. And we use the PTO to couple it up to the speed of the pump. And this transmission allows us to vary the pressure and volume that we're injecting with, which is extremely important because depending on what depth we're operating at, depending on the lithology we're trying to inject in, depending on if we're trying to generate formational breakdown within a fracture, we need to vary both pressure and volume depending on where we're injecting through an interval. Here's a look at the back of the truck, the control center. You can see we've got a lot of gauges, readouts. We've also got a tablet there that's connected to some of the telemetry, and also our operators' headsets as well are connected. So we can talk about what we're seeing both at the back of the truck and at the borehole. I'll pull this up real quick. This is just an example. I mentioned a second ago about utilizing the PTO on the truck. And really, this is kind of as simple as just shifting gears. Whatever we need to alter our volume, our flow rates, we can change the RPM by adjusting the gears that are running the pump. And this is what allows us to ramp up, to maximum, volumes of 300 GPM, maximum gauge pressures of 2200 PSI. And just as a side note, not that we would ever need downhole pressures that great. We're not trying to crack or frack the rock here. We want to maintain the fracture, the feature we're injecting in. We want to get formational breakdown within it, if we're doing a pump up bleed off test. But we're not trying to crack rock here. That's not the objective. That's not where your contamination is residing. It's not residing in new fractures you're generating. So that's not something that we want to do with this. Kind of unique to this whole setup, the way this was designed is the inlet side of the pump will allow us to maintain product suspension, the way the valves and the seats are engineered. We've had those set up to tolerate a wide range of materials. Obviously here today we're talking about both Boss 100, Boss 200, Cat 100 products, which are true slurries, but this can also be used for other applications as well, where we're not targeting petroleum or CVOC compounds. There we go. This next slide is an example, and then this is what I was getting at a few minutes ago, is the versatility of this pump, this truck setup. here we are. This isn't our packer setup, but this is a tip. This is just showing you some examples of flow rates that if we were to use this, you know, in an unconsolidated setting, what we could get in terms of pattern, in terms of, you know, subsurface thrust. You can see there once we get up to 250 GPM, you get a really nice spray pattern. You know, if this was unconsolidated material, you'd be getting radial mixing away from some of that. Here's a little overview just showing you exactly what we're, you know, putting through on this tip here. Again, this would not be for bedrock. I'll show you a shroud setup on one of our injection packers here in a second, but this is just to show you some of the generative force we can get in situ to achieve distribution, because that's really the biggest thing we're trying to do with this whole, you know, tip to tail design, is to show you that distribution is a big reason outside of characterization why bedrock sites don't typically go as smoothly or as successfully as people think they should or do in the field. So here we are loading up the shroud onto one of our injection packers. You're going to see the water start to come out here in a second. The shroud does a couple things. It protects the injection inlets. It also reduces some of the directional turbidity that hits the formation directly. As you can see there, it says it needs to be gentle. That's important here. Again, we're not trying to destroy the interval that we're working in, but we do need flow and we do need pressure to get distribution. Bill, I think I'll hand it off to you for the installation monitoring.
Yeah, thank you, Derek. I'll take from there. Yeah, so getting back to some of the features or the principles that we utilize during the characterization part, we're going to employ during the implementation as well. During the injection within a specific borehole point, we're going to look at sentinel wells with transducers to assess and verify connectivity. We're going to take that straddle packer that Derek was just showing and talked about. We're going to lower that from top down into the borehole. And as we're going down the borehole, we're going to isolate specific selected intervals that we identified from all the RDC processes and initiate a clean water or freshwater test. We're going to get into some plots of that here in just a minute to talk about. And the whole purpose of initiating a freshwater test is to determine the specific interval's ability to accept fluid and to help with us to adjusting our batch design to put the right fluid volume in based on what we're seeing on pressure signature and distribution within the surrounding formation, looking at the transducers. And using these freshwater injections on the way down help us to ultimately determine where we're going to install the remediation amendment. In this case, we're talking about the trap and treat products here. As we then come back out of the hole and are initiating slurry injection within these specific intervals. Next slide, please, Derek. So getting into some graphs here, some graphics here, I do want to recognize Mr. Ray Boyle, senior hydrogeologist with us that has spent several decades in the bedrock injection field, and he has taken a large data set from his injection history to look at properties of specific rocks and what it takes to actually inject in these materials. And so some busy slides here, but what I really want to get across to everybody is looking at the different color codes you can see based on the legend on the right. We're looking at metamorphics, claystone, plutonic, or limestone. And you know, it's like Derek was saying, we're not trying to frack rock. We're not trying to induce new porosity within the formation. We're actually increasing the permeability or the connectivity of the existing secondary porosity features. And so what this illustrates here is that we want to show is that the bulk of the injection work that we do falls under this, what's called the formation resistance. It's a normalization of the injection characteristics of looking at PSI over GPM. And so the bulk of the injection work that we do falls under this 50 formation resistance factor quotient that's come up with here. And so what this is really telling us is that that I want to share with everybody is that based on a data set of, I think it's 445 data points, the bulk of these geologic materials fall within an acceptable range for actually accepting fluid. Next slide, please, Derek. And so taking that last slide, and rather than breaking it out into geologic material, we're just going to lump all 445 data points into a common data plot under a single variable. Looking again at this PSI per GPM quotient on the bottom axis. And again, what you can see, just kind of a simplification of the previous slide, is that all of these data points fall to the left skew of this particular plot here. And again, this will be more important in a subsequent slide coming up. But I just want you to kind of keep this picture in your mind that we're shifted left on this particular normalization of these pressure metrics or these injection metrics that we're monitoring while we're working within a specific formation. Next slide, Derek. And so then on this final data point, taking those, or this final data plot, we've taken those 445 data points and we're pulling out the gallon per minute variable. And so what this is now showing us is the PSI required to initiate breakdown and for the formation to accept fluid flow. And as a general kind of SOP or standard operating procedure, when we're looking at these individual intervals with freshwater test injections, when we get to that 1200 PSI margin, it's kind of our go or no go on being able to assess if that interval is able to accept fluid and go further with any sort of remedial injection. And again, as you can see from the data here, the bulk of these data points fall within that left portion of the graph here and under that 1200 PSI margin. There are some points beyond that. As we move into the next slide, Derek, please, this is why the Triplex and the capability of this pump is so important, and why this tool is so unique in the capability of what it can accomplish for the remediation field. And so if you look at the photo on the right-hand side, this goes back to the downhole camera image that we showed on the video earlier at this 59.2 foot vertical interval. This is a basaltic formation up in the northeast. And this particular borehole, this fracture here, or this plane here at 59.2 feet, freshwater test injection was initiated and reached that upper limit of 1200 PSI. And that freshwater test injection was just essentially barely weeping into the aquifer. And so the main objective here was to see, well, what happens if we put the bigger pump to it and see if we can develop that fracture better. So again, we've got this quotient that I mentioned, the formation resistant quotient on the vertical axis to the left, which is PSI per GPM. This helps us to normalize for this particular plot purpose. And so what you can see is that ramping the big pump up to a 34 gallon per minute reaches that threshold of 1200 PSI, where the formation opens up and the pressure bleeds off to a next data point where flow is initiated again. And what happens then, as the pressure drops off, we can initiate additional fluid volume, additional flow, for the purpose of getting distribution within the formation. And so when you reach the final plot on that first graph, or that first line series, as you see, we're now going into the aquifer matrix at 72 gallons per minute, but the pressure has now dropped off to a more manageable 750 GPM or PSI, which is down in that more acceptable range for us to be able to initiate slurry injection. We move up now to the next data point on the next line, and this is where we've made a BOSS 200 slurry, and we're now going to introduce a denser material into the formation for the purpose of getting distribution out laterally across that specific interval. And so now we've gone back to our 34 gallons per minute. We're at 680 PSI, and as we essentially begin to add slurry and add volume to the formation, the pressure begins to drop off. But as we've learned through the years, or through the purpose of doing these remedial injections with slurries, is that we need to maintain somewhere around 300 to 400 PSI on the formation in order to maintain good distribution and know that we're getting out into the formation. So as this pressure is dropping off, we need to increase the flow rate in order to maintain good distribution and getting out into the formation. So the next three data points show that drop off but increased flow. the lighter gray line is where we've switched gears. Derek showed the chart earlier, so it's finishing what's left in the batch tank and increasing flow rate as the pressure's dropping off. Moving to the green line, this is finishing out the injection at an interval for the designed amount where we had to batch up and do a new batch change. But again, as you can see, when we initiate that injection, we're now down at that 34 GPM initiation, but we're only at 200 PSI. And as we ramp up to the 72 GPM, we're now going into the formation at 500 PSI. So you can see that needing this variability to make sure that you can adapt to the changes as you're moving through injection is critical to making sure that you get this material out into the formation in the way that you want and how far you want it to go. And just as a side note, our typical injection volume on a site ranges somewhere between 150 and 200 gallons of prepared slurry. Next slide, please. All right, so we just wanted to highlight our portfolio of work to date. I was enjoying updating this series of slides because I got to the point where I said, wait, we need to have 2 separate pages here now. So this was a nice exercise in itself. And what we want to do is just roll through here is look at, I've got items color coded. And what we want to look at here is time frame of when these were performed, the geology, and the type of contaminant we're dealing with, and regionally where they fall out. So the red is going to be sites that have been completed and have achieved a no further action. Sites have reached site closure. The blue on this particular page is going to be sites where some form of pilot scale has been initiated and full scale is being weighed and evaluated for being implemented. Next slide, please. And then these plots here are these itemized sites. The green is going to be your full scale completed and you're in some sort of performance monitoring. And then the black line or the black rows are going to be sites that have been approved and are in some phase of either upfront RDC work or approval process. And just some breakdown of metrics on the bottom. Total 27 sites we have on the portfolio thus far. You can see the breakdown as I've itemized with the color coding. And on the right-hand side, just some metrics for you as far as the types of geology that we're involved in to kind of complement the graphs that Ray Boyle had prepared several years ago. And then you can see based on the geology, we're primarily in carbonates, but we are getting the other rock types out there, geologic types, more frequently. Next slide, please. And then distilling this data down a little bit more to visually see it, where it falls out regionally within the domestic US. Next slide, please. All right, so we'll finish up here with a case study. This is a site that I worked on, location in South Central Tennessee, former gas station. It's currently a mixed residential commercial facility. It's within the Crab Orchard Mountain Group geologic setting, Pennsylvania sandstone overlying a limestone with a very thin layer of sandy clay on top of the bedrock. Next slide, please. So the initial conceptual site model that came across at the time of review, site has LNAPL and benzenes above the SSCL site-specific cleanup level of 887 ppb. And you can see the green isocontour on the right-hand side map. The benzene and NAPL plume essentially mirror one another within the 2 wells, MW1 and MW6. Overburden impacts were non-existent. Soil bedrock interface was only about 3 feet below grade. And there was no perched water within that overburden. Bedrock at the time of initial review ranged anywhere from 11 feet to 27 feet, depending on which well you were looking at the facility. And groundwater concentrations of specifically benzene was anywhere from 2.29 ppm to 5.94 ppm in the groundwater. Next slide, please. So as part of the Bedrock RDC and the recommendations on this site here, the final plan approved for actual implementation, this was one of these sites where access was limited and surface geophysics did not proved to be cost effective or beneficial to the process. So 3 open boreholes were proposed. The green points on the map you can see identified as IW1, IW2, and IW3. These points were installed again as open borehole wells with surface casing, total depth completion at approximately 36 feet below grade. Next bullet, please. And then we employed downhole geophysics in this instance, looking at optical televiewer, caliper, and fluid temperature and conductivity. The optical televiewer, the water clarity was very, very high quality. It was really good for looking at the OTV. You can look at your planar features on the plot here and noticing a distinct void zone at the lower portion of the plot here. You can also see the caliper is valuable for seeing that variability in bore aperture. Next bullet, please. Then employing, again, as we talked about during the RDC part of this presentation, doing the aquifer characterization, using the straddle packer to initiate pump tests and discrete interval sampling, as well as transducer data logging. Next bullet, please. And then finally, the results coming out of that helped us to have a better handle on what was really going on at the site. You can see from the cross section here, if you can remember the site map, this is a plot, or this is a cross section running roughly from the southeast to northwest, running through all the wells at the northern port of the building there. You had LNAPL occurrence and higher benzene concentrations of around 5 to 6 ppm, strictly within the well screened across or right at that interface of the overlying sandstone on top of the limestone. And then you have a lower concentration zone that's more dispersed at depth within that limestone aquifer, which correlated more to a deeper water-bearing element, whereas in the shallow zone you had a perched element, which you can see here base graphically. Next slide, please. So some of the things, looking at the data, you can continue to learn as you're moving through the process. Looking at the plot in the field of this specific instance of pumping on injection well 1 and looking at that perch zone within MW1. Looking at the initial plot in the field when it first comes off, the instrument, it doesn't look really all that impressive, but there's this kind of blip here highlighted by red within this particular time frame. And if you'd advance 1 click forward, Derek, please. Taking the raw data and plotting that specifically and changing the scale, but then lining it up with our timestamp and field information from what we were doing at the time of that specific interval, we see there's some interesting geometry here. And what we noted here while working on this specific well is that the response didn't really, the response in the adjacent well while we were working on the injection well or the characterization well didn't really come from the pumping, but rather from introducing a 300-pound packer slug into the aquifer. So essentially performing a giant slug test on the injection well had a significant influence when both lowered into the aquifer and inflating those elements, squeezing the water, and then a respective response from that adjacent well when deflating the packer and lowering to the next adjacent interval. So noting that there was some connectivity between the perch zone as well as the to the deeper lying, more continuous aquifer was quite obvious when looking at the data and very interesting to see. Next slide, please. And then getting into more of what you would typically see with a pumping test, with a step-down pumping test. When we're doing these testing aquifer characterization methods, we're going to initiate pumping at a specific interval at a roughly half a gallon to 1 gallon a minute flow rate for the purpose of purging and developing that interval and then eventually sampling. But then when we get to the end of the sampling interval, we're going to induce a stress test where we're going to ramp the pump up to somewhere between 3 and 4 gallons per minute and try and really stress the aquifer and see what the surrounding matrix looks like or how it responds to that pumping. And so in this specific instance here, you can see this nice step-down curve of initiating at the lower flow rate, but then increasing at the higher flow rate within the pumping well versus the adjacent well. Next slide, please. So taking all the characterization data back, coming back to the table with an updated design, and defining the final goals of what the accomplished plan was for out here in remediation at this site was to eliminate the occurrence of the LNAPL within the 2 wells adjacent to the residential property, taking the bedrock groundwater plume to reduce it under SSCLs, and over the course of performance-based monitoring to show a downward trend in all contaminants of concern to move it closer to site closure. Next slide, please. So again, the final injection plan, utilizing those 3 characterization points for the purpose of remedial injection, taking all the data from the characterization, we were able to vary the injections between points, and we're dependent upon the significance of the geology encountered within that hole. The BOSS 200 loadings were calculated based on the contaminant demand of both benzene and TBPH, since we were dealing with LNAPL. And then we were basing our initial injections on aperture of the bore of the intervals that we encountered to try and get a feel for how much fluid volume we wanted to induce on that specific interval. And then looking at those areas where we had fairly good coverage and definition, we were wanting to make sure that we had enough safety factor in there. So we had a 2 safety factor on the 2 wells beyond the building, but then put an added measure in the one adjacent to the building because of the unknown mass emanating that was unknown beneath the building itself. And we'll see that that's the path of transport here in just a minute. Next slide, please. So getting into the final wrap up of the presentation here, just again, looking at the data after the fact, well, during and after the fact, but some of the highlights that we see when we actually plot this. Again, looking at, we talked about the methodology for going down the borehole for injection. Our initial process is to work our way down the borehole and feel out the individual intervals with freshwater injection. This is just looking at a freshwater plot, or a plot of freshwater injection in injection well 2, and you can see the individual vertical lines indicate intervals of induced freshwater injection and the response of the hydraulic influence in injection well 1. So we're looking at one injection well in reference to the adjacent injection well to see what kind of response you get from the initiation of that freshwater injection. Next slide, please. And this is an interesting slide I wanted to call out. So I mentioned the unknown mass beneath the building, and I want to call out the blue plot on the upper part of this here. So we're injecting in the same well, injection well 2, and we're monitoring several hydraulic head changes within different wells across the site. And of interest here, monitoring well 2, which is shown on the site map being to the south-southwest of the area that we're working. During the initial phase of work out here, the site was assessed for multi-phase extraction. Magnet helix response and MW2 showed a vacuum response, and so we were interested to see what kind of response we would get in MW2 during injection. And what we can see here is that a direct pathway to the UST system, which is the rectangle in purple, side gradient 90 feet. So during slurry injection, when we're adding larger volumes of fluid in the injection well, down gradient at the area of influence that we're trying to remediate, you can see a direct head change response in a side gradient well almost 100 feet away back in the direction of the original source. Next slide, please. And then to finalize, or to get down to what everybody's really interested in on remediation, is the performance of reducing contaminants at the site. And so this site was implemented in late summer last year, so we're not too far into the monitoring period, but data looks very promising initially here, and we're going to continue to watch it to see how it performs. We've already reached remedial goal number 1. LNAPL in the source area is eliminated. We're not seeing any occurrence of LNAPL anymore. And you can see here the site-specific cleanup level for benzene is plotted horizontally as purple. Red line is benzene. Black vertical line is the initiation of the BOSS injection, BOSS 200 specifically. And the blue line is TDPH, which is your indication of total contaminant mass in the dissolve phase. And so you can see that we've dropped the contaminant levels to below the SSCL immediately following injection, and we're maintaining those standards and should see this continue to trend downward with subsequent monitoring events. I think they're due to sample next month, if I'm not mistaken. Next slide, please. Shows the other well, MW6. This is a little more favorable plot here. This one we've added sulfate to the plot for the purpose of showing the relationship between contaminant reduction and terminal electron acceptor response, as the terminal electron acceptor being consumed to sustain the biodegradation. That's the second half of the trap and treat process associated with the carbon injection. So similar plot here. Horizontal line is the SSCL, vertical line is the Boss injection, and then you're looking at benzene and TVPH versus time with the addition of sulfate. With that, I believe that wraps up the case study here. I'll pass it over to Derek.
Thanks, Bill. Before I turn it over to our moderator, Mike Mazzarese, I just wanted to say again, thank you everyone for your time. We're going to move to a Q&A session here. If you can stay for that, great. It looks like there's a number of questions already populated. If you haven't entered your questions, please do so at this time in the question box. Just as a quick reminder, in case you have to go, we are offering the same presentation again today at 2:30 p.m. Eastern. So if there's a colleague or an associate or friend you think may benefit from some of this information, we certainly appreciate you passing that along to them. And then our final webinar, number 8, will be next Tuesday, same times, 11:30 and 2:30 Eastern. That's going to cover injection of PRBs into overburden and bedrock for similar applications that we've talked about both today and in other presentations. So without further ado, if you have to go, thank you. If you could stay, our Q&A sessions have generally been pretty well attended, and we've gotten great questions. So Mike, if you're on the line, if you want to jump in.
Yeah, Derek, can you hear me?
I can, Mike.
All right, great, thank you. Okay, so we have quite a few questions, and we're a little over on time, so we'll probably we'll have Bill and Derek answer questions for about 8 minutes or so, and that'll wrap us up at about 60 minutes. And then we will, if we don't get to your question, we'll follow up with you directly afterwards. So I guess kick things off, Bill and Derek. So someone asked if if you've got a weathered rock unit on top of the competent unit, how would you address that using this technique, or how would, because would our packers applicable in that situation?
Eric, you got it? You want me to get it?
You can do that. You probably deal with that more than I do.
Yeah. So if you're dealing with a weathered unit on top of a more competent unit, it's all based upon borehole competency. And so in one of our previous webinars that was given, we talked about an over-drill technique or a pre-drill technique, where if you can't maintain the borehole to remain open for the purpose of using straddle packers, you can utilize the pre-drill technique to essentially clear the borehole, seal it with bentonite, and then come back in with traditional lower footprint, smaller impact, direct push rig, and trip back through with direct push tooling and inject that way. And you would do this on a grid array versus more points over top of a consolidated unit with less density points.
Okay, thank you. Other one is just about depths, and I guess depth limitations, and maybe I think something that I could add to that is how deep we've gone on that portfolio that you showed earlier.
Yeah,
well, I think.
Go ahead, Derek.
I was just going to add. I think the biggest limitation is the tooling itself. I mean, every site's going to be specific to the unit you're operating in. In some cases, the amount of equipment you can get if it's a remote site, but really the biggest limitation is the equipment. So if we can get in there and we can do some of the RDC process and evaluate the uptake on a feature, fracture, certain, deep intervals, say 250, 300 feet down, we've got the capacity with that Triflex pump to handle it. So it then becomes, at that point, going through the RDC process and evaluating access and applicability. So, I don't want to say we can get every site, but really with the equipment we've got, there's a lot of ways to overcome what are traditional limitations. going back to one of the things we talked about early on in this presentation, because we are isolating very unique intervals, and they are typically, again, 18-inch, very small, unique intervals in the subsurface. We don't have some of the limitations where if you're doing, low pressure, high volume, low pressure, low volume injections, where you're looking for dissolution into the water column and preferential uptake by the formation, that's where you get limited very quickly. If you're just trying to tremie something and diffuse it into a borehole. Since we're not doing that here, I don't really think we're terribly limited in a lot of cases. So I think we have a young geologist on staff that said, if you can drill it, we can get to it. Probably the best way to put it.
All right, thank you. All right, so next question. Is there additional benefit to using surface ER surveys in fractured rock other than mapping the formation top? In your experience, can weathered or fractured zones of bedrock be identified using surface-based ER?
This is Bill. I'll take that. So yeah, the superficial methods are quite beneficial in more instances than just borehole siting or finding top of rock or specific geology or an indication of geology. And that's why I wanted to mention the IP as being one of the options to couple with the ER. Is that with the electrical response, there's indications of biological activity, fluid flow and transport, potential presence of NAPLs. So the surface geophysical methods help provide an indication for some of these other items that we may be interested in. The primary purpose is for helping to get a better handle on contaminant fate and transport based on the geology, but then some of the other pieces of information that come out of that can help to refine that even better and add some better resolution to it before you start poking holes.
Okay.
I think that answers the question, I hope.
Yeah, thank you. So someone asked to just clarify the purpose of the shroud that's used.
Sure. So, the shroud serves two purposes. There's an injection shroud, there's a sampling shroud, and both are situated somewhat differently. For sampling purposes, the shroud, since that is one continuous packer, is part of the interval of isolation, but it's also to protect anything that would come out of the formation in terms of silt, sand, gravel, what have you coming up, being sucked into the string itself. So that's the first one. I think secondly, you're probably focusing on the video where we have the yellow, the cylindrical shroud. That really serves a main purpose of protecting the flow coming out of the bore string from directly hitting the formation. Again, we need gentle, we need high volume, we need high pressure. We don't want to directionally blast a formation because, as I said earlier, we're not here to crack rock. We're here to utilize those existing features and fractures. We talked a lot about what you would call high pressures, looking at some of the PSIG in previous slides. And while that is something that's definitely achievable, in terms of the pressure that's hitting the formation, we don't want to climb up that high in terms of exit pressure. We would certainly start to crack rock. In the majority of sites we would deal with, once you start getting up towards 1,000 PSI or more, they're going to start to break down. Excuse me. So the shroud does two things. It helps us regulate the force on the formation, and it also, from a bigger standpoint, helps us to maintain the competency of that feature fracture that we're injecting on.
All right, thank you. I think we'll stick around for two more, and then and then again, the rest of these, we'll go ahead and just reach out directly. And so one refers, Bill, to the aquifer response charts that you showed. And the question was the head monitored in a specific interval in the adjacent boreholes, or was it in an open borehole?
For that site specifically, it was monitored with a specific head elevation. I don't call that out. The graphs are busy as it is, but they were lowered to specific depth intervals within the borehole. That interval was not monitored or modified throughout the process, but rather once the data elevation was set, it was maintained throughout the entire pressure test, or the entire, whether it's a pumping test or an injection test. So hopefully that answers your question. If not, let me know.
Yeah, I guess, and the last one is just talking about ROI. So, as it relates to, really ultimately well spacing for a given site. And I know it's gonna be variable, but maybe just speak on based on our prior experience.
Sure. So, ROI is going to be very site specific. And that's part of the reason we do the RDC process. One of the things you saw in some of the slides Bill talked about, we're not just looking at pressures and flow rates, we're also looking at transducers placed in sentinel wells around the well that we're focusing on. And that's showing us response. And that's also showing us ROI as well, and connectivity. So, in a perfect setting, you can get some pretty expansive ROIs using this triplex setup. A standard set would typically be to put your injection centers somewhere between 30 and 50 or 60 feet apart. We've had a few locations in the Northeast where we've seen ROI as great as 100, 125 feet away from the injection well that we're, and we knew that because we had some, a road cut there and some weeping that we had to monitor. So, if you've got good connectivity, there's enough horsepower in that setup to really push product into that feature fracture and get really good distribution. And at the end of the day, that's the biggest thing we're trying to achieve here is distribution, because low flow, low volumes of loading of reagent aren't really going to cut it for a lot of the sites you're talking to us about when it comes to remediate in Bedrock. So distribution's king, and that pump really allows us to get it there.
Yeah, I just want to add to Derek's piece. I think he hit it home at the very end there, talking about distribution is key. Each site is specific, and we're going to vary the injection metrics based on what we see. It's not static. We're going to modify it based on how the site's performing and how the formation's responding to the fluid being introduced or the slurry being introduced. But it's more about distribution than ROI. So that gets back to that plot that I showed with the PSI versus GPM normalized as a quotient, and showing the variable pressure versus flow rate to maintain a sustained pressure and flow within the formation to get out and away from the point of injection to carry that material, not just along a preferential flow path, but specifically along the permeability or the porosity feature that we're trying to target and remediate.
All right. Well, I think we'll wrap up there, guys. I'll hand it back over to you guys to send us off. And again, thank you, everyone. I see that most of you have stuck around. Those of you that we did not get to your questions, we will reach out to you shortly.
Thanks, Mike. And so again, thank you, everyone. From all of us at AST and RPI, we appreciate your time. The contact info for both myself and Bob, two entities that can immediately help you after this presentation, is on your screen. And you can also reach out to us through social media or our brand new website at astenv.com. So thank you, and everybody have a great day.
Thank you, everyone.